Hello. Today I want to talk about the specifics of how to get a TensorFlow model actually on an NPU running, or how to get it running on an NPU, rather than talking about a specific project or a specific demo. Just more giving you an overall glimpse of how to do it, but also like our experience and generally talking a bit about NPUs. Yeah, first of all, I will start off with talking a bit about my employer, but not too much. We don't want to make it about a commercial here. So it's just that you get where I'm coming from. I also talk a bit about myself. Then I'll talk about the embedded hardware. What type do we have? What type do we use? And then how actually the next chapter to run a TensorFlow model on this embedded hardware, specifically how to run it on the NPU. Here we talk about quantization, about the NPU itself, and also on measurements. After that, we talk about what is important if you're looking yourself for a chip, an NPU chip, an AI accelerator. What are the key points actually to look out for? And last, we'll talk about the FPGAs and edge devices, or training on the edge, sorry, because that are questions I rather get quite frequently. Yeah, so about Fighttech. Fighttech is an international embedded hardware developer and producer. And very important here, so headquarters in Germany, but also production is in Germany. So if you are looking for embedded hardware produced in Europe, yeah, we can help you with that. We're happy to solve your problems together. And we have long time experience, like over 30 years we're in the business, and luckily because of that we have a lot of customers ranging from small companies to large companies or to enterprises, and also in every field. So we have knowledge in all different kinds of technologies and solutions. So quite likely it will also fitting for your company. Yeah, just to mention, because we're working with an NXP board here, we are alpha partner of NXP, meaning that we get really early access to their devices, but we also help them a bit like debugging their BSPs, etc. And whenever we find a bug, we report back to them. So it's a giving and taking, right? Yeah, about myself. So my name is Jan Weert. I did my PhD in electrical engineering, focusing mostly on signal processing. So I've over 10 years of experience in signal processing. And in 2013, I started mainly with machine learning and deep learning. And I worked mostly with patient data analysis. So like the difficult data, you could say. Yeah, and now I work for Fighttech as a data scientist, kind of advising our customers like how to actually go forward, solving the problems with data-driven approaches. Yeah, what we're talking about is the Fireboard Pollux, and this incorporates actually the i.mx 8M Plus. Here on the left side, you can see all the components of that kit. But for me, most interesting is the neural processing unit, right? So the neural processing unit is specifically for that, integrated by NXP into this i.mx 8M Plus, and yeah, we facilitated that and used it actually quite successfully. And yeah, how did we do that? Or how do you now get a model on that hardware? That is actually the main question, right? The thing is, we are actually quite lucky because NXP did a tremendous job in creating EIQ. It's a kind of machine learning library from them, who creates a connection between your model and the NPU. And it natively supports TensorFlow Lite, and it also supports ARM-N, which means over ARM-N you can use PyTorch, ONNX, and this is what they have on their website, at least what they're stating. But actually, if you're looking in ARM-N, ARM-N supports also MXNet and Café and many other things. Almost all model libraries you will need are supported. So you have to still check out if everyone is also supported now as an NPU, but at least for TensorFlow Lite, PyTorch, or ONNX, I can guarantee this is supported. And so what you have to do. So I personally worked a lot with TensorFlow, so of course I choose the TensorFlow Lite way. And so what you have to do is you have to transform your model from TensorFlow to TensorFlow Lite, because TensorFlow itself, the core library, is not supported, only TensorFlow Lite, which is kind of a slimmed down version of a TensorFlow. So, and then that's the only thing you have to do, because the NPU of the NXP board is or needs integer 8 values, meaning that internally, so normally if you train a model with TensorFlow, you would have the weights, the bias, the activations, everything is in float 32 position. But here we need integer 8, meaning you have to quantize the model. What happens here is you have like a very good precision. You have to squeeze that these values into a smaller number field, you could say. Probably wrong word, but so yeah, you only have like the 2 to 255 integer values. Now we have to squeeze that in, and of course you will lose some precision. There are two different ways you could do that. Either with post-training quantization. You will use that if you already have a pre-trained model, and now you decide, you know what, it would be nice to have that on embedded hardware. Or you just play it around on your device, you train your model, and you say like, now you're ready. Let's get that to the embedded hardware, get that to TensorFlow Lite. Then you would use post-training quantization. On the other hand, if you use like if you freshly start from scratch and you train your own model with your own data, you can also use quantization over data. And the difference is here that the error is less high with quantization over training. Actually, almost zero. It is actually zero, you could say. While post-training quantization, you have a bit of an error, but actually the difference is really minimal. On the TensorFlow side itself, they state it's around maybe 0.5% a loss of precision. So it really depends what you need, right? But it could be that you say, no, we work really hard for each percent point, for each half percent point of precision. Yeah, and then you should go for quantization over training. So let's take a look at the code. This would be now post-training quantization. So yeah, first of all, so what you do is, depending on the TensorFlow version and depending on how you actually have your model, in this case, this line represents now that you would work with TensorFlow 2.x, so for example 2.3, and you want to convert a previously saved Keras model, which is saved in a H5 file. And then you could just like say from Keras model file, but then because Keras is actually also from a previous TensorFlow version, you have to use this V1 version. There are different ways to do this if you have different TensorFlow versions, and also how you save your model. You can do that from protobuffer file, H5 file, but also just a freshly generated and compiled model. So please go to my Medium landing page. That would be janweert.medium.com, and there you'll find an article about like how to quantize a model to run it on an NPU. And there are different versions. I think the title is a bit different, but you get it. You will find it, and it's about, you have different TensorFlow versions, you have different saved models. Like how would you actually convert that, and how would that result in different models? So next point, interesting point here is that you set actually the supported types to integer 8, and then you can set the inference in and output type also to integer 8. What you have to do is here you have to set the representative data set because, as I said before, you have an error when converting from float 32 to integer 8. You will have an error, meaning I want to eliminate that as far as possible. And the point is, so we have to squeeze the float values into this new number room of 0 to 255, or at least into 255 values, depending on integer 8 or unsigned integer. And here you give them actually the images either you trained your data set on, or if you either don't have them, or you say like, I know that I will actually work in a different environment, the images might look a bit different, so you give them the values which you will expect, the images you will expect, talking about images here or data in general, and then the representative data set will actually tune the change of weights, the adaptation of weights to the input values, that the error gets more or less minimal. We did it here with a data generator. You create a generator and then you yield one image after another and push that to the converter. So if you do that, what you actually get are two different model types. Here on the left side, you see a model which was converted either with a TensorFlow version below 1.15, or you set the in and output values not to integer 8. You just left that part out. And what you will get a model where the input is still float 32, but then you have, as you can see here on the left side, you have actually a quantization layer in there. And this quantization layer, if you look at the details here on the right side, you can see that the input is the float 32 of that quantization layer, but the output is integer 8. And you have the same thing at the end, like a dequantization again. Input is integer 8, output is then float 32. Then on the right side, you see the same thing. And this actually works at the moment only with TensorFlow 2.3. There was a bug in 2.2. I don't know if they changed that already. Anyhow, it was 2.3. You can set the in and output values also to integer 8. And what you will get is that you can see here the information on the right side. Here the integer, the input is already also integer 8. And in this case, also the output. But be aware, or let's say that the output, if you set the output to integer 8, meaning your output is an integer 8, meaning the precision can be much lower. We created a fun demo actually where your face would be compared with a celebrity face, and it worked quite well actually. But when we use the quantization also for the output, we get superb drop in performance, because actually suddenly the output values would be embeddings, like just floating point values, 2000 of them. Suddenly they were not in floating point precision anymore, but with the integer precision, and then the comparison between pictures went really off. So for each problem there's a specific solution, so be aware if you can set or not your output to integer 8. The same as integer busy. The input is also interesting. So for example, normally, because you train your model in TensorFlow, then you work most likely in float 32, but also your pre-processing is most likely in float 32. So it might make sense to have also the input in float 32, because you will use the same pre-processing function on your embedded device. But for example, if you use the MIPI camera, which is included actually in the Fighttech products kit, if you order that, you'll also get a MIPI camera. This actually gives you, I think it's int 8 or unsigned int, I don't know, at least one of the two. I think it's unsigned integer. It gives you unsigned integer values directly. So that is the question. If we take just the raw data, if you don't transform anything, it might be easier to have also an integer 8 input, so that we can directly take the input stream. Just saves you a bit of time. But you have to figure that out for your problem. Just wanted to make you aware of that. So now let's talk about quantization aware training. So I said before, if you want to really the highest precision you can reach with quantization, you should do a quantization aware training. What you do is actually you set your model. Oh, I forgot to input that slide. Actually, I forgot to show you actually the line of code, but it's actually like 2 lines of code. You have to import a library and then set your model to quantization aware training. And meaning what happens there, automatically these fake nodes are introduced. So and what happens here, so these fake nodes that represent the error you will later get while converting, or not converting, like quantizing, right? Meaning, so you put that error in, and then you start training your model. So you train your model while having this quantization error already in there, meaning looking at your accuracy or kappa value or whatever you use as performance index, you can see that your model is training well. And if you are satisfied with the performance of the training of the model, you can stop the model, and that will be the precision you will also get after quantization, because the quantization array was already in your model, right? And you took that into account already. So this is how you would do that. But again, when you would have to retrain your model, you can also, of course, do that with a trained model already. You can do like transfer learning with that. That could work here as well. So now let's take a look. Why do we need quantization, right? I said before, we need integer 8. I said we'll look at that later. Now we are here. So what are NPUs? Why are they so fast? That's a good question, right? So the point is, it's all about the arithmetics. So floating point arithmetics are much more complex than integer 8 arithmetics, meaning also the physical device, a floating point unit, is much more complex than an arithmetic unit. So we can use a smaller and simpler arithmetic unit, which leads to less power consumption, less heat development, but also it's smaller, meaning you can put more onto that, on the same space on your embedded device. And that pushes your speed, or it boosts your speed to get these super fast tops and super fast embedded systems, right? Now I'll talk about fast. What does fast mean? So here you can see 2 different measurements. So we had the resonant 50 network, and we run inference on input images of 2 to 4 times 2 to 4, and you can see that the mean inference time with loading the model, etc., was 16 milliseconds. While running this on the GPU actually gave us a mean of 1.56 seconds. You can see, so if you calculate it, it's around 96 times faster to run this deep learning network, the ResNet 50 in this case, on the NPU instead of the GPU of this embedded device. Down here you can see this table, and you can see that so the first line is actually from us. This is the ResNet 50, but here down here NXP on their website they state they trained actually MobileNet V1, V2, and the inception model, and they get actually different inference times here as well. So we have the inception model is roughly the same from the size as a ResNet 50, so we get roughly the same inference time. But then the MobileNet, of course, it's much lighter and much faster by general already. So of course here it runs much faster with around 3.3, 3.4 milliseconds. Really nice. We actually working on benchmarks here to get our own values because, yeah, I never trust another source, but I trust NXP here. So then you might see like, what is that? There's a rubric called warm-up time. What is happening here? So if you look at the warm-up time, you can see that actually with the ResNet 50, we got 70 seconds of warm-up time, right? And even with the inception, 42 seconds. So it's actually quite a lot. What is that? So warm-up time means the first time your model is loaded into your system, into your cache, your RAM, and memory, that takes around 70 seconds, right? This is actually quite a long time. And the problem here is if you're thinking of like something like Wake on LAN or something, that might be difficult here with 70 seconds, but luckily, if you store your compiled model on your memory, you can actually reduce that drastically to around, in our case, 8.8 seconds, which is fine also for Wake on LAN, or even with the smaller models to around to 2 seconds. The thing is here also it really depends on the size of the model. Even with an uncompiled model, say if you get with the mobile nets, you already get only 10 seconds. So yes, so you have to consider this. Of course, you have to look at your memory in general because you're storing that in memory. That can lead, if your memory is limited and your application is huge already, it could lead to instability. So again, for each problem, a different solution. You have to look what is happening here. And I think very strongly that NXP is working on that because 70 seconds for this raw setup is not acceptable for at least for most things. But just to make you to easy up, it's just really just the first time. So the first time you boot your system, the first time it takes 70 seconds. Afterwards, it takes 16 milliseconds, just to be don't alarm you. So yeah, the overall experience we had with the i.mx 8M Plus, we have to say, so today I have to say the experience was really good. So it's very, very easy to convert your TensorFlow model to TensorFlow Lite and quantize it and put it on the NPU. It's running directly. So I have to shout out to NXP. They did a tremendous job on this. EAQ is working really at the moment flawlessly. Perfect. Thanks a lot. Yeah, but in the beginning, so just retrospect. Oh Jesus! Wow, I'll skip that word. There were some errors in the NXP BSP, and actually we had some blood and tears until we found out that it was not our error, but on the NXP side. And then, but as soon as we reported this bug, they changed it immediately. Again, shout out to NXP. Really fast communication. And I mean, this is our role also as alpha partners, right? So we have to find the bugs in the early versions, suppose the alpha version of the BSP, and of course you have to expect some bugs. So really well done, and now it's working really well. Yeah, and also we found a error in the TensorFlow 2.2 model with the in and output quantization, as I mentioned before. Now we're using just TensorFlow 2.3. It's not a problem there anymore. I don't know if they changed that in 2.2, but anyhow, just use the latest version of TensorFlow. You should be fine. Then also PyTorch ONNX over ARM and N. Actually, we didn't check that at the moment. We have a partner in Berlin, Numetri. They're looking into that at the moment. I don't have the results yet, but as I know, NXP most likely will go also quite flawlessly. We just have to remember how it is working is that NXP, they adapted the NNRP, which is a library from Google, and they use that to facilitate models on Android phones. And NXP adapted that to facilitate, so to get the communication going between the model and the NPU. And of course, as NNRP is from Google and TensorFlow is from Google, of course, the TensorFlow models it's working more natively, you can say here. And this RMNN was built in later from NXP. So yeah, it can be expected that's a bit bumpy at the road, but again, I'm quite certain it also will work really flawlessly if it's not already working perfectly. So now I want to do some comparison also between two chips, because I just only talked about the 8M Plus, but there are many chips out there, but I will talk about the Gyrfalcon because I worked with the Gyrfalcon before, and yes, I'm also a fan of the Gyrfalcon. It's a really good chip. So now I want to compare the two, and yeah, and please don't mistake me if I'm now taking like the one versus the other. It's actually not like one is better than the other, like and one is crap and the other one is the perfect. No, it's more like they're different and they each have their different role, and I just want to explain both of them, and you can see for yourself, or I try to explain which role they're fitting and when I would choose which one, and also why we actually in the end we stick to the 8M Plus, and at the moment at least not the Gyrfalcon. So because if you look at the raw numbers, you can see that the 8M Plus has 2.3 tops in raw speed, while the Lightspur 2083S 2803S, sorry, from Gyrfalcon has 16.8 tops. So raw power, much faster. And you have to say, this is the fastest chip of Gyrfalcon at the moment. And you have to look also at the power consumption. The power consumption of the Gyrfalcon is only 700 milliwatts. Wow. While the i.mx Plus, we measured the whole system during inference. We had 1.4 watts. And okay, we have to say the comparison is not completely fair because, again, as I said, we measured the whole system. Of course, also CPUs probably increase performance. Every GPU is running as well. While the data from the Gyrfalcon chip was from the data sheet where you only have the power consumption of the chip itself. So yeah, most likely in the whole system, the Gyrfalcon also will increase the power consumption of the whole device a bit more. So a bit more comparable here, but still, I just want to say, like, Gyrfalcon still with this amount of tops, and this was 700 milliwatts. That's just fantastic, to be honest. But they're more than just raw power. So looking at the implementation, to be honest, like as I said before, I was really pleased with the EIQ of NXP. This was really a flawless working. And to be honest, back in the day, at least, it was quite some month ago now that we worked with the Gyrfalcon. At this point, it was a bit of a hassle to transfer your models. A bit more also to implement the chip on the embedded device, a bit more difficult than with say 8M Plus. But of course, NXP is like a dinosaur in the business, right? They know how to implement a chip into their design. So yeah, no, we have to expect that NXP is doing a better job here. But anyhow, so just from raw working with that, it was a bit more smoothly with NXP here. But also EIQ supports just a bit more of the model library. So we have the TensorFlow Lite, PyTorch, ORNX, and if like the RMNN, there are many more like MXNet, Café, etc. While the Gyrfalcon only, in quotation marks, support TensorFlow and Café, which is good. I mean, there's also really main things, but at the moment they only support those two. More importantly, here is actually that with the 8M Plus, you actually supported. You can use kind of any model you want to. You can use this convolutional neural network, recurrent neural networks, but also the classic machine learning, which you can do in TensorFlow as well. Not only scikit-learn, but let's say you can use it there as well. While with the Gyrfalcon, it's only convolutional neural networks and actually only VGG, ResNet, and MobileNet architectures, which is also fine because, man, these are the three biggest ones. And I mean, that's also why they get so fast, because, man, they focus the performance of those three networks. Of course, that's how they get to super speed. So if you have a ResNet architecture, for example, and say, oh, we just need speed, we just implement it once and then we're fine, you can go with a Gyrfalcon. While if you want to be a bit more versatile, here, this is more interesting to look at the 8M Plus from NXP. But yeah, the key point actually why we chose the 8M Plus was actually not all the other values, but it was the last point, long-term availability. So we talked to Gyrfalcon, and at that point back in the days, they could not guarantee us long-term availability. As I said, I think if I remember correctly, like we can guarantee you a 1 year, maybe 1.5 years, but we do not know what's happening. And the market is really fast in this area. We are a Silicon Valley company. Maybe Google comes around next year and say, you know what, your chip is great, we're just buying you, and then all your contracts are void. So we cannot guarantee that. And our customers actually, they depend really on that. They depend on long-term availability. We have a lot of industrial partners. Actually, all of our customers are industrial partners, I think. Yes, they want to run a system and they want to know that they can run this for the next 10, 15 years and get replacement parts and get support for that. So that was the main key point why we chose actually to continue with the 8M Plus. So generally, there's also questions on now, okay, the one is much faster than the other. So when do we actually need these TOPS? When do we need this raw power? That's also a good question because, I mean, it seems a lot of difference, but personal opinion, I think the 2.3 are enough for quite a lot of tasks. So when do you need this huge amount of top? That will be with really high resolution images. If you have a 4K image, you want to analyze that, of course, you have a lot of input dimensions and suddenly you need more tops to go through there. But the point is the actual bottleneck here would most likely not your tops, but your memory, because you have to put your image in memory, and a 4K image is really relatively large, and then you have the model in there and you have your application in there, and I don't know, maybe some data you have to compare to or whatever. So you have already a lot in your memory, and the question is, can you put more into more? Do you have enough space in your memory, especially on an embedded device where you do not have like 32 gigabytes of RAM or something, but more likely 2, 4, 8, right? So this would, yeah, that'd be one thing. But yes, there's one thing, one part where you really need more TOPS, and this is real-time critical applications, also security applications. I'm thinking mostly of autonomous driving. So if you mean in autonomous driving, you have to know like this under a millisecond, you want to know if there's a child on the street, right? And this in 360 degree with good resolution, you want to analyze actually every single pixel of that image to see what's happening there. And yes, then you need this raw power. Then I would not recommend the 2.3 TOPS of the 8M Plus here, or definitely recommend the Gyrfalcon, for example, or others in this region. But yes, so another point is large batches. People say like, hey, with a lot of TOPS, you can have larger batches. But the thing is, large batches, you actually mostly need only during training. While during inference, you mostly have only batch size of 1, meaning like you analyze one image after another. So also here on the inference side, on the embedded world, you don't need that much TOPS. While you can use those chips during training as well. Of course, Azure, for example, you're using also specific chips for training. Another point would be, of course, multi-stream input with high FPS. I mean, we get with a 2.3 TOPS, we got over 60 FPS for one stream. You can have multiple stream with a fiber pole. So I think 2 cameras are directly supported. And you would be able also to have a relatively high FPS with a multi-stream input. But of course, if you have more cameras and higher resolution and as there are more FPS, yes, you need more TOPS, of course. But I would say the main bottleneck actually is the surrounding software. If I think back of the demo with the faces, celebrity face we compare, we noticed that like the demo itself, if you look at the face, your face would be detected, then they find out who you are. Yes, the inference actually took only 60 milliseconds, but the whole thing to actually show you then the results took around a second. Meaning, yeah, you have pre-processing. You have, I don't know, like the building up your pipeline, then you have to find your result, then you do something with the result of your inference, right? And then, for example, plot a picture or something. So meaning the surrounding software probably is much more a bottleneck than the TOPS of your chip, right? You have to be able to feed your chip with enough data, with enough pre-processed data that it actually can work, in this case, with 16.8 TOPS, right? So you have to have a crisp, clear surrounding software that you can actually use all the TOPS you supported here, just to make that clear. So maybe to summarize that a bit, so what to look for when you're looking for an NPU, I think you should look for the TOPS fitting the requirements, right? Then also, I like it that a wide variety of supported models are available. That it's not like just one type of architecture or two, but actually all of your models, because I mean you have a lot of pre-trained models in the network, in the internet, something you can download that, use that, reuse that, not inventing the wheel new, wheel new, Jesus. And so therefore, it's really nice that everything's already supported. Also, the ease of implementation of the model is also, for me, not that unimportant, because you put otherwise a lot of effort, time, energy into actually bringing your model onto your device instead of developing your application, developing the model, etc. But you're hanging just by getting your model run on the device. So the better that goes, the more the faster you are with the development, to be honest. Yeah? So it's not that unimportant to have that. Long-term availability, I said that before, at least for us, it's quite important. Price, yes. Power consumption, heat development, these are really points, of course, to look out for. Yeah, and now I want to quickly also look into FPGAs, because I'm actually asked relatively often about FPGAs. I'm not an expert on FPGAs, I have to say that, but at least what I know, they are relatively expensive. They can get quite a lot of TOPS as well if you get a dedicated FPGA for that, but again, very expensive. Like the bang for the buck is really not that good. Yes, and the thing is, a colleague of mine told me that you have to calculate, like, for the same power as a CPU, you have to calculate about 10 times the cost for the FPGA. So you have to have really a dedicated problem that fits. But the second problem is actually also that it's really difficult to program. It's not that straightforward. Then you have to pay the license for the tools to debug and to implement your code on the FPGA, which are also expensive. So yes, you need at least more people. You need more people as well, right? You have to have the data scientist who creates your model. Then you have to have a dedicated person who programs your FPGA. I mean, for example, Azure does that. Azure has FPGAs dedicated for training neural networks. But Microsoft, they have a lot of people. They can just dedicate a couple of guys, say, you know how to do FPGAs, just focus on that. And for specific dedicated problems, yes, there might be an FPGA which is just perfectly fitting, and it's better than an NPU. But in general, I would say, no, I would not go the FPGA way. Just you have to have a really specific problem here. So for the last slide, training on the edge, that's also a question I relatively often get, because people, there's a misconception a bit, like it's a self-learning system, right? So I put the system somewhere, I get them, for example, a video input, and it just learns by itself. That's not really how it's working. Mostly you will train your model beforehand, and on data you gather, data you actually pre-process. That's actually really long and an important part of the AI history, or AI project, more or less, getting your data ready. But so then you train your model, and if you are satisfied with the performance of your model, and you actually recheck the model if it's working in the wild, let's say, if it's working as well as during training, then you deploy it on the edge. And to be honest, at the moment, when you use a TensorFlow model on the NPU and you run TensorFlow Lite, it's actually not possible to train, because TensorFlow Lite does not support the fit function for training. But please check the roadmap. They stated that they want to look into that, to training also with TensorFlow Lite. So yeah, they might be coming up with that. So of course, yeah, it might be possible there was a Gyrfalcon, to be honest, because they support TensorFlow, core TensorFlow, I think. If I'm correct, please check that. And then you should also be able to train. But keep in mind, is training on the edge really necessary for you? Because what happens is you have a finished model, and you just get new data, but you cannot confirm that new data. So you have to write a really elaborate algorithm to check the data, and then also to check if the data if the model is trained well. So it's much better, much more secure, and actually the better way to do, to get the data home, analyze the data again, retrain a model, and as soon as you're satisfied again and you recheck your model, if it's really working well, then you deploy an update via example Azure or a RAG server or something like that. So we have that as well in Fighttech, update services. So then you just redeploy your model, and then you're kind of on the safe side, because you want to know what your model is doing, and you want to know what it is training on. So just to say that. But if you really need to train your model on the edge device, then again, look for TPU, for example, Gyrfalcon, which can support, for example, core TensorFlow to do that. And what you should look like would be transfer learning, that you don't retrain the whole model, but just train ahead of the model. It's really low effort, because I mean the performance of this embedded hardware is not comparable to, for example, a virtual machine in Azure or something which you can just rent. Yeah, I hope that most of your questions are answered. Thank you for listening. If you have any more questions, you can anytime contact me on my email, j.wrth@fighttech.de, or you can go to LinkedIn. Just Google me, Dr. Jan Wert on LinkedIn. You should find me. Yeah, and of course go to the Fighttech site. This is actually the main page is what with .de Germany, but we have also internationally China, India, United States, a lot of daughter companies. Yes, so I do give workshops on the topic of machine learning. I can help you to facilitate your specific problem, and we can find a data-driven solution here, and then we can implement this data-driven solution on an embedded hardware. We will help you with that. We have experts on all fields, Yocto BSP, whatever you need, just contact me. I'm looking forward to talking to you. Have a nice day.